Your Claude API bill is 10 times higher than it needs to be, and Anthropic just proved it themselves. In their official BrowseComp benchmark, a hybrid setup pairing Claude Haiku as the executor with Claude Opus as the strategic advisor didn't just match Opus alone performance, it doubled it, 2 times the benchmark score. And the cost? Down 85%. That's not a community hack. That's not a Reddit optimization trick. That came straight from Anthropic's own engineering blog. The uncomfortable question is, if the model provider is publishing this result, why are the majority of Claude API developers still calling Opus on every single step of their agent loops? By the end of this lecture, you will have a concrete formula, a pattern you can drop into your existing pipeline today to capture that same 85% cost reduction without sacrificing a single point of output quality. Let's make the waste viscerally concrete. Imagine a typical agent loop, 10 steps. Retrieve context, plan subtasks, call a tool, validate output, revise, call another tool, synthesize, format, review, finalize. A developer who hasn't seen that BrowseComp result falls to the obvious choice, Opus on every step. After all, Opus is the smartest model, so why risk quality? Here's the cost reality. Opus input tokens run at $15 per million. Haiku runs at 25 cents per million. That's 60 times cheaper per token. In a 10-step loop processing 2,000 tokens per call, a single Opus-only run costs roughly 30 cents. Run that 10,000 times a month, which is modest for any production size, and you're looking at $3,000 monthly just in model inference. Now apply the advisor pattern. Haiku handles 8 of those 10 steps. Opus only touches the 2 that require genuine strategic reasoning. Same loop, same output quality. Monthly bill drops to under $400. That's the gap we're closing today. But here's what most developers get wrong about where to actually place Opus, and it's not where you think. When Anthropic published this result, it didn't stay quiet inside developer Slack channels. It hit Geek News, the Korean developer community's closest equivalent to Hacker News, and pulled 29 upvotes within hours. For a highly technical API implementation detail, that's a significant signal. Why did it go viral? One reason: the implementation friction was nearly zero. The entire advisor pattern is activated single API request header. No new SDK. No infrastructure change. No model fine-tuning. Just one header, and your agent loop restructures its model routing behavior. That one header detail is what separated this from academic benchmark noise and made it immediately actionable. Developers could read the blog post, add the header, and see their cost dashboard change by end of day. But here's the trap that the viral post didn't warn you about, and it's exactly what we'll dismantle in the next section. Let's be precise about what this lecture will actually equip you to do. Because vague, you'll understand AI better promises are a waste of your time. By the end of 6 chapters, you will be able to make 3 concrete decisions in your own production system. First, identify which exact steps in your agent loop qualify for Opus-level reasoning versus which can be safely delegated to Haiku, and you'll have a decision rubric, not just intuition. Second, refactor your existing agent loop to implement the advisor split, including how to pass strategic context from Opus down to Haiku without token bloat eating your savings. Third, measure your actual cost delta before and after, not estimated, not benchmarked on someone else's workload, but instrumented against your own token usage logs. These are not soft skills. These are engineering decisions with a dollar figure attached. But before we get there, we need to establish who this lecture is actually designed for, because the advisor pattern has a prerequisite that most tutorials skip entirely. Who is this lecture built for? Specifically, you are already calling the Claude API in a production or near production environment. You have an agent loop, maybe LangChain, maybe Llama Index, maybe a custom implementation, and you are already paying a Claude bill that shows up in your AWS or Anthropic console every month. You are not here to learn what an LLM is. You are here because you suspect your architecture is costing more than it should, and you want a concrete pattern to fix it. If you're a Claude API developer managing an AI SaaS product, or an ML engineer owning an internal agent pipeline, this lecture is calibrated exactly for your decision altitude. One prerequisite to be explicit about: you should be comfortable reading Python async code, because the live implementation demo in Chapter 3 works through actual API calls, not pseudocode. If you're coming from a product or architecture role, the pattern logic will still be fully clear, but the code walkthrough moves fast. In Chapter 2, we'll go deeper on why the single model loop is architecturally broken, not just expensive, but structurally limited in ways that no prompt engineering can fix. That's the insight that makes the advisor pattern feel inevitable rather than optional. Let's rewind to 2023. The first wave of LLM agents was simple: one model, one loop, every task handled by the same endpoint. GP4 or Claude is doing everything, from planning the strategy all the way down to formatting a JSON output. It felt powerful. It was also architecturally naive. By 2024, developers started adding tools, web search, code execution, retrieval. But the core loop stayed the same. One flagship model orchestrating and executing everything in a single thread. Then something changed. Practitioners started noticing that 80% of the token spend was on tasks that didn't need a PhD-level model. Simple extraction, format conversion, condition checks. The insight that emerged was not about prompting better, it was about routing smarter. Multi-model heterogeneous architectures were born, not from research papers, but from engineering teams staring at their API bills. So before we talk about the solution, we need to understand exactly why the single model loop is broken at its core. And the answer is more structural than you might think. Here is the core architectural flaw, stated plainly. You are applying maximum reasoning capacity every single subtask in your pipeline, regardless of whether that task actually needs it. Think about what a flagship model like Claude Opus is optimized for: nuanced multi-step reasoning, handling ambiguous edge cases, synthesizing conflicting information, generating novel plans. Now think about what your agent actually spends most of its time doing: extracting a date from a string, checking whether a URL is valid, formatting a JSON blob, deciding if a retry threshold has been crossed. These are not the same cognitive load. Sending Opus to format a JSON response is like hiring a neurosurgeon to take a patient's blood pressure. It works, but the mismatch is grotesque. The technical term I use for this is cognitive load mismatch, and it manifests directly as token waste. Because Opus doesn't just reason more accurately, it also generates more tokens doing it. Longer chain of thought, more elaborate responses, more hedging. For complex tasks, that's a feature. For trivial tasks, it is pure cost overhead with no quality return. The question then becomes, how do we match task complexity to model capability precisely? That's where the cost numbers become undeniable. Now let's make the cost gap numerically undeniable, because this is the moment where abstract architecture talk turns into real engineering decisions. As of 2024, Claude's pricing per million tokens breaks down like this. Claude Haiku 3.5, the fast, lightweight executor, runs at roughly $0.3 input and $4 output per million tokens. Claude Sonnet 3.5, the mid-tier workhorse, sits at $3 input and $6 output. Claude Opus 4, the flagship reasoning model, costs $5 input and $5 output per million tokens. That ratio sink in. Opus input tokens cost nearly 19 times more than Haiku. Output tokens are over 18 times more expensive. If your agent loop calls Opus 100 times per user session for tasks that are 80 to Haiku appropriate, you are paying an 18 times premium on the majority of your compute. This is not a marginal inefficiency. This is a structural tax on poor architectural decisions. The pricing table is not just a billing artifact. It is Anthropic telling you in dollars that these models are designed for different jobs. The next logical question is, what does Anthropic itself say about which model belongs in which role? And the answer is more explicit than most developers realize. Here's something most developers miss entirely. Anthron research and documentation doesn't just sell you these models as better or worse versions of each other. They explicitly frame them have distinct cognitive roles within a system. Opus is not Haiku but smarter. Opus is an advisor, a strategic reasoner. Its design is optimized for tasks requiring deliberate, slow thinking. What cognitive scientists call System 2 processing. Novel problem decomposition, identifying edge cases that simpler models would miss, synthesizing ambiguous inputs into a coherent plan, and making high-stakes judgment calls. Haiku, by contrast, is an executor, fast, reliable on well-defined tasks. System 1 thinking. Given a clear instruction, it retrieves, formats, extracts, or routes with remarkable accuracy at a fraction of the cost. The architectural implication is critical. You should never let your executor make planning decisions, and you should never waste your advisor on execution tasks. This maps directly to how high-performing human organizations work. Senior architects design the system. Junior engineers implement the well-specified tickets. The question is whether your current agent pipeline respects this division of cognitive labor. And most don't. Let's look at a real research task to see exactly how this plays out. Let's make this concrete with BrowseComp, Anthropic's own benchmark for evaluating web research agents. BrowseComp tasks look like this. Given a complex research question, the agent must browse multiple web sources, synthesize findings, and produce an accurate answer. On the surface, it feels like an Opus all-the-way problem. But look at the actual task structure. The agent needs to first understand the research question and decompose it into a search strategy. That is a genuine planning task requiring Opus-level reasoning. Then it needs to execute 10, 20, sometimes 50 individual web searches, evaluate each result for relevance, extract key information, and decide whether to continue or pivot. Those repeated search, execute, extract cycles. Each one is a well-defined, low-ambiguity operation. It doesn't need Opus to check if a search result is relevant. It needs speed and cost efficiency. Haiku territory. Finally, the synthesis step, combining findings into a coherent answer, sits back in Opus territory. So a browse comp task naturally decomposes into one Opus planning call, n haiku execution calls where n can be 20 to 50, and one Opus synthesis call. If your agent uses Opus for all n intermediate steps, you are paying Opus rates for tasks that Haiku handles with equivalent accuracy. That's the waste, and BrowseComp makes it visible. But how do we formalize which tasks go where? The answer requires a complexity spectrum framework. Now let's build the mental model that ties everything together before we see the actual architecture. Tasks exist on a complexity spectrum, and each point on that spectrum has an efficient model match. At the low end, deterministic operations, string parsing, regex matching, template filling, Boolean condition checks. These don't need a language model at all in many cases, but if you're using one, Haiku is already overkill. One tier up, structured retrieval and extraction, pulling named entities, classifying a document into predefined categories, formatting API responses. Haiku handles these at near-Opus accuracy for a fraction of the price. In the middle, moderate reasoning tasks, summarizing a document, with nuance, evaluating whether a business rule applies to an edge case, generating a response that requires contextual judgment. Sonnet lives here. At the top, genuine complexity, designing a multi-step plan from ambiguous requirements, identifying failure modes in a proposed system, synthesizing conflicting sources into a defensible conclusion. This is where Opus actually earns its statistical per million input tokens. The brutal truth is that most agent loops spend 70 to 80% of their compute budget on the bottom two tiers, while paying top-tier prices across the board. Now that you have this complexity map in your head, the next chapter shows you exactly how the advisor pattern enforces these boundaries in code, and the architecture is simpler than you'd expect. Here is the core insight that changes everything. The advisor pattern is not about using one powerful model, it's about separating the act of thinking from the act of doing. At the top tier, Opus receives your high-level goal. It doesn't execute anything. Instead, it uses extended thinking to decompose that goal into a structured plan, a list of discrete, well-specified subtasks. Each subtask is a JSON object with clear inputs, expected outputs, and success criteria. That plan gets handed down to Haiku, which runs each subtask in a tight execution loop. Haiku doesn't think strategically, just executes faithfully. This is the two-tier control flow. Opus is the architect, Haiku is the contractor. The cognitive labor is priced accordingly. And here's the part most developers miss. Opus only fires once per goal, not once per iteration, which is exactly where the 90% cost reduction comes from. But wait, how does Opus actually communicate that plan to Haiku without ambiguity? The answer is a specific API parameter you've probably never touched. Let's get concrete. To unlock extended thinking on Opus, you need exactly one change at the API layer, a beta header. Without this header, Opus runs in standard mode, competent, but not using its full chain-of-thought reasoning engine. With it, Opus enters a deeper deliberation mode, where it can internally explore multiple approaches before committing to a plan. The head is Anthropic beta. Interleaved thinking to me 25 for 18th. You pass this in your HTTP headers on every Opus call that's performing the advisor role. Then in the request body, you set thinking to enabled and define a budget tokens value. This controls how many tokens Opus can use for its internal reasoning before it writes the output. A typical advisor call uses a budget of 8,000 to 16,000 thinking tokens. That sounds expensive until you realize this fires once, not per loop iteration. The math changes entirely. Now, what exactly does Opus produce inside that thinking budget? That's where the JSON schema becomes critical. Here is where the architecture becomes rigorous. When Opus finishes its extended thinking phase, it needs to output a plan that Haiku can consume without ambiguity. Ambiguity at this boundary is the most common failure mode in multi-model systems. I've seen production pipelines break because Haiku received freeform instructions it couldn't reliably parse. The solution is a strict JSON schema for subtask specifications. Each subtask object contains 4 mandatory fields: a unique task ID, a task type from a controlled vocabulary, a structured inputs object with all data Haiku needs, and a success criteria definition. Optionally, you add a complexity score and a timeout. This schema is what makes the advisor pattern robust. Haiku doesn't need to interpret intent. It just maps the task type to an execution handler and runs it. The intermodal protocol is the contract. Break the contract and the system breaks. Enforce it, and you get deterministic, auditable behavior across thousands of Haiku calls. Now, what happens after Haiku returns all those results? The closing loop is simpler than you think, but it's where the final quality lives. The closing loop is elegant in its simplicity. Once Haiku has processed every subtask in the plan, all results are aggregated into a single structured payload. This payload is passed back to Opus, not for more extended thinking, but for synthesis. This second Opus call is much cheaper. Standard mode, low token count, just pattern matching and assembling the final answer from validated component results. Think of it like a general receiving battlefield reports and writing the final briefing. The thinking already happened up front. The synthesis is rapid. This two-phase Opus usage, heavy thinking at the start, lightweight weights at the end, is the cost optimization the architecture is built on. You're paying for Opus intelligence exactly twice, once to plan, once to finalize. Everything in between is Haiku territory. This is the complete advisor cycle. But what happens when a subtask is genuinely too complex for Haiku? That's the question that introduces the three-tier architecture, and it changes the cost equation in ways that might surprise you. The two-tier pattern works beautifully for tasks where subtasks are genuinely atomic and well-defined. But in practice, real-world goals decompose into subtasks with wild different complexity profiles. Some subtasks are trivial: extract this field, format this string, call this API. Haiku handles those perfectly. But some subtasks require moderate reasoning. Classify this ambiguous document, resolve a conflicting data point, generate a nuanced summary. These are too complex for Haiku to handle reliably, but complex enough to justify routing back to Opus. This is the exact problem the three-tier architecture solves. You insert Sonnet as a middle executor, a reasoning-capable model that costs significantly less than Opus per call. The stack becomes Opus as the strategic advisor at the top, Sonnet as the reasoning executor for moderate subtasks in the middle, and Haiku as the workhorse for simple execution at the bottom. Each tier earns its place by handling a specific complexity band. The question is, how do you decide which subtask goes to which tier? That requires a routing mechanism, and it's simpler to build than you'd expect. The routing classifier is deliberately lightweight. If it were complex, you'd need a model to route the router, and that's an infinite regress problem. Instead, you extract complexity signals directly from the subtask JSON spec that Opus already generated. Remember the complexity score field we defined in the schema? This is where it pays off. The routing logic checks three heuristics: the complexity score from the spec, the task type against a predefined complexity map, and the number of conditional branches in the inputs object. Based on these signals, each subtask gets routed to Haiku, Sonnet, or flagged for Opus review. The classifier runs in microseconds. It's pure Python, no model inference. The routing decision is deterministic and auditable. You can override it per task type if you observe quality degradation in production. This is the key engineering insight. The routing logic lives outside the models, which means you can tune it without retraining or reprompting. Complexity classification is a business logic problem, not AI problem. But here's the question you should be asking: does adding Sonnet actually save money, or does the middle tier eat into your cost advantage? Let's look at the numbers. Let's put real numbers on the three configurations, so you can make an incision, not a gut feel one. Configuration 1. Opus plus Haiku. This is the maximum cost efficiency setup. Opus fires once for planning, Haiku handles all execution. Estimated cost for a 100 subtask workflow. Task success rate on well-defined atomic subtask, 91 to 94%. See, it's fast. Haiku is quick. Configuration 2. Opus plus Sonnet. You replace Haiku with Sonnet for all execution. Cost jumps to roughly for the same workflow. Success rate climbs to 90 to 98%. Use this when subtask quality is non-negotiable. Configuration 3. Opus plus Sonnet plus Haiku, the hybrid. The ring classifier sends simple tasks to Haiku and complex ones to Sonnet. Cost lands at roughly double the Haiku-only setup. You reclaim the quality on the tasks that needed it. This is the configuration most production systems converge on after tuning. The Haiku-only config is where you start. The hybrid is where you land. The Sonnet-only config is for high-stakes domains where errors are expensive. So which one is right for your project? The decision tree coming up will make that call explicit. Let's consolidate everything from this chapter into a decision framework you can apply immediately. The choice between 2-tier and 3-tier comes down to 3 questions. First, are your subtasks consistently atomic and well-defined? If yes, Opus plus Haiku is your starting point. Maximum cost efficiency, no routing complexity. Second, are you observing failures on a specific subset of subtasks in production? If yes, profile those failures. If they cluster around moderate complexity task types, introduce Sonnet routing for exactly those types. Don't add the middle tier wholesale, add it surgically. Third, is your domain high stakes enough that a 3 to 4% quality delta justifies a 3 to 5 max cost increase? If yes, use Opus plus Sonnet across the board and optimize later. This is the architecture chapter. You now understand how the advisor pattern is structured, why the API parameters matter, what the intermodal contract looks like, and how to scale from 2 to 3 tiers based on real cost-quality trade-offs. What comes next is where it gets real. We're going to implement this entire loop in live Python code. And I'll show you the 3 failure modes that take down most first implementations before they ship. Alright, theory is done, hands on the keyboard now. The architecture we walked through in the previous chapter looks elegant on a whiteboard, but the real question is, how many lines of code does it actually take to wire this up? The answer will surprise you. It's under 150 lines total. Let's start with the project skeleton. You'll need the Anthropic Python SDK version 0.25 or later, because that's when the extended thinking beta stabilized enough for production use. Run pip install Anthropic and grab your API key from the Anthropic console. The critical piece most developers miss is the beta header. Without explicitly passing betas interleave thinking 25, May 14th, on your client instance, you will get structured thinking blocks back. You'll just get a normal response and wonder why your cost savings disappeared. We set this once at the client level, and every Opus call inherits it automatically. Notice we're creating TWO separate client wrappers here. One for Opus with the beta header, one for Haiku without it. Haiku doesn't support extended thinking, and you don't want it to. Keep them separated from the start, or you'll spend an hour debugging a 400 error later. Now let's implement the heart of the pattern, the advisor function. This is the only place Opus gets called for planning, and every architectural decision you make here has direct cost consequences. We pass the user's high-level goal, and we set a thinking budget of 8,000 tokens. Why 8,000? Empirically, that's the sweet spot for decomposing tasks into 3 to 6 coherent subtasks without over-engineering the plan. Go lower and the plan is shallow, go higher, and you're burning tokens on second guessing. The response comes back with interleave thinking blocks and text blocks. We only care about the text block, specifically, a JSON object describing the subtask array. Here's where most tutorials skip a critical step. You must validate that JSON strictly. If Opus hallucinates a malformed plan, and it occasionally will, your entire downstream executor chain fails silently. We use JSON loads inside a try except, and if parsing fails, we retry the advisor call once with an explicit respond only with valid JSON suffix. 1 retry budget, no more. The cost of a failed Opus call is still cheaper than cascading executor failures. What happens when Haiku receives a poorly scoped subtask? That's exactly what the next function handles. The executor function is where volume lives. This gets called once per subtask, potentially dozens of times in a single session. So every line here has a multiplied cost impact. We send the subtask spec from Opus's plan, which includes a task description, expected output format, and any relevant context, directly to Haiku. The key discipline. We enforce a rigid results schema using a system prompt that says respond only, with a JSON object matching the schema, nothing else. Haiku is remarkably good at following strict format instructions when the schema is simple, but remarkably good is not perfect. We need retry logic here too, but implemented differently from the advisor. For the executor, we use exponential backoff with a maximum of 2 retries, because Haiku failures are usually transient formatting errors, not reasoning failures. If it fails twice, we log the failure and return a null result. The synthesis step will handle missing data gracefully. Notice the result schema is minimal, just task ID, status, and output. Don't let Haiku pad its responses with explanations. Token bloat on the executor side is where the cost savings quietly evaporate. This skeleton now production ready. Let's wire everything together. Now we assemble the main agent loop, the orchestration layer that turns 2 isolated functions into a working system. The synchronous version is trivial. Iterate over the task list from Opus, call the executor for each, collect results. But synchronous execution has a hidden cost that most teams don't account for. Latency multiplies. If Opus generates 6 subtasks and each Haiku call takes 800 milliseconds, you're waiting nearly 5 seconds sequentially for work that can run in parallel. This is where Asyncio changes the economics. We convert both the loop and the executor to async, then fan out all subtasks concurrently using Asyncio gather. Wall clock time for 6 parallel Haiku calls drops to roughly the time of the single slowest call. Your cost in tokens is identical. You're not saving money here, but you are saving the developer time and the user experience degradation that makes teams abandon async architecture prematurely. One important guard: if your subtasks have dependencies between them, Task 3 needs the output of Task 2. You need a dependency resolution step before fanning out. In practice, a well-prompted Opus plan will explicitly mark independent versus dependent tasks. We check the depends on field and partition accordingly. Independent tasks go parallel. Dependent chains run sequential. This hybrid approach is what separates a production advisor loop from a demo. Here's the feature that will actually change how your team makes architectural decisions. Real-time cost tracking. Not estimated, not ballpark. Actual tokens consumed and actual dollars spent per call per session. We instrument every API call to capture the usage object from the response, which gives us prompt tokens and completion tokens separately. Multiply by current pricing. Opus input is $15 per million tokens. Output is 75. Q input is 80 cents. Output is $4. And you get per call cost to the 5th decimal place. Accumulate these in a session-level ledger. At the end of every run, you get a cost report that shows you exactly what you spent, broken down by model. But here's the more valuable number, the hypothetical baseline. What would this exact task have cost if you'd sent everything to Opus? We estimate that by summing all executor token counts and repricing them at Opus rates. That delta, real cost versus hypothetical Opus-only cost, is your savings proof. Show this number to your team lead. Show it to your finance team. This is the number that gets the advisor pattern approved for production. When you're seeing 87% cost reduction on a realistic workload, that number speaks louder than any architecture diagram ever could. And speaking of realistic workloads, let's close the loop with the final Opus synthesis call. The final step closes the loop, the Opus synthesis call. After all Haiku executors have returned their results, we send everything back to Opus, but this time Opus is not thinking deeply. We disable extended thinking for the synthesis call by setting the thinking budget to 0. Why? Because synthesis is not a reasoning problem, it's an assembly problem. Opus's synthesis job is to take a structured array of completed subtask outputs and weave them into a coherent, well-formatted final answer. That requires language quality, not deep reasoning. Disabling thinking on the synthesis call alone saves you another 30 to 40% on that final Opus invocation. Synthesis prompt is critical. It should include the original user goal, the Opus-generated plan, for context, and all executor results in a structured format. Do not just dump raw JSON at it. Format the results as a numbered list with task labels. Synthesizes is markedly better when the structure mirrors the plan it originally created. And there you have it. 1 Opus planning call, n Haiku execution calls, 1 Opus synthesis call. With thinking budgets precisely tuned for each role, the skeleton is complete. Now let's actually run it and see what the cost report looks like on a real query. Let's run it. The test query. Analyze the competitive landscape for vector database startups in 2024, covering funding, technical differentiation, and enterprise adoption trends. This is exactly the kind of multidimensional research task where the advisor pattern earns its keep. Watch the console output sequence carefully. This is the live execution trace. First, Opus generates the plan in about 4 seconds. You can see the JSON land, 5 subtasks, each with a clear description, expected output type, and dependency markers. Tasks 1 through 4 are independent. Funding research, technical comparison, enterprise case studies, and pricing analysis. Task 5, the trend synthesis, is marked as depending on all 4. So the executor fans out tasks 1 through 4 in parallel. All 4 Haiku calls resolve in under 2 seconds total. Remember, parallel wall time equals the slowest single call, not the sum. Then task 5 runs sequentially, using the outputs of the first 4 as its context. Finally, the Opus synthesis call runs, no thinking budget, and produces the final answer in about 3 seconds. Total wall clock time, approximately 9 seconds for a task that would have taken a naive sequential Opus-only implementation 30 seconds or more. Quality of the answer. We'll discuss that in the next chapter's benchmark section. But first, look at the cost report. Here is the cost report. Read it slowly. Every number here is real, pulled from actual API usage objects, not estimated. The Opus planning call consumed 312 input tokens and 680 out tokens, including the thing blocks. Cost, approximately $0.047. The 4 parallel Haiku executor calls averaged 80 input and 99 output tokens each. Combined cost, $0.00007. Opus synthesis call, no thinking, consumed 8,440 input tokens and 920 output tokens. $0.097. Total session cost, $163. Now look at the baseline column. If you had sent the exact same task, with the same total information processed to Opus exclusively, using the same token volumes repriced at Opus rates, the estimated cost would be $0.47. That's an 88.99%, nearly 9 times cheaper. And this is on a 5-task decomposition. As task count scales up, 10, 20 subtasks, the Haiku volume grows while the Opus bookend costs remain roughly constant. The savings ratio improves with scale. The one counterintuitive insight here, the synthesis call is your second largest cost driver, not the planning call. That means if you want to further optimize, shorten the context, pass to synthesis, not the thinking budget. is your next lever. Remember that when you're tuning in production. Let's close out the implementation chapter with a quick repo structure overview. Because knowing which functions are drop-in reusable is what determines how fast your team can actually ship this. The project is deliberately flat. Advisor.py contains call advisor and call synthesis. Executor.py contains call executor and its async wrapper. Loop.py contains the main run advisor loop orchestrator. Cost tracker.py is completely standalone. You can drop it into any existing Claude project today without touching anything else. Here's the reusability verdict. If you already have a Claude agent, you don't need to rebuild from scratch. Wrap your existing main prompt in call advisor. Wrap your existing response handler in call executor, and add the synthesis step at the end. The pattern is an overlay, not a replacement. The functions we built today handle the 80% case. The remaining 20%, streaming responses, tool use integration, memory across sessions, those are extensions, not blockers. The code is available in the linked repository. However, before you deploy this to production tomorrow morning, there is one chapter you absolutely not skip, the benchmarks chapter. Because the 88.9% savings we just saw comes with conditions, edge cases, and at least 2 scenarios where this pattern will actively hurt you. That's next, and it might save you from a very expensive mistake. Alright, we've built the loop, we've seen the code, but here's the question every senior engineer should be asking right now. Where does the benchmark data actually hold up, and where does it fall apart? The browse comp results are real, but they're not uniformly real across all task types. For complex multi-hop research tasks, the advisor pattern delivers close to a 2x improvement in success rate. We're talking 40% on the hardest retrieval chains. For medium complexity tasks, gap narrows to roughly 1.3x, and for simple single-step lookups, the delta is statistically negligible. The data is telling you something important. This pattern is not a universal performance upgrade. It's a targeted tool. The question is whether your task distribution actually lives in the complexity zone where the gains materialize, and that breakdown is coming up right now. Now let's talk about the cost that nobody puts in their blog post headline. Latency. The advisor pattern introduces an Opus planning call before your executor even starts working. That planning call alone can take 3 to 8 seconds depending on task context size. For a long horizon research task that was already going to run for 90 seconds, and 5 seconds of planning overhead is a 5% tax, totally acceptable. But here's the reversal. For a task where a single haiku call would have answered the question in 1.2 seconds, you've just made the user wait 6x longer and spent more money doing it. This is the latency trap. 2 Opus calls in the loop means you're compounding that planning overhead at every major decision point. Of applications, customer-facing chatbots, real-time recommendations, anything with a sub-2-second SLA. Need to think very carefully before adopting this. But wait, is latency always the killer constraint? The answer depends entirely on one variable. So what's the actual threshold? Let me give you a concrete decision rule. Because vague advice is useless in production. The advisor pattern breaks down, meaning cost exceeds benefit. When your task can be fully specified in a single prompt with no branching. When the expected output is deterministic and short, and when there's no intermediate state that needs to be evaluated between steps. Think, translate this sentence, classify this support ticket, extract the date from this string. These are single-step transformations. Haiku alone handles them with 80% plus accuracy. And adding an Opus planner on top is pure overhead. You're paying for strategic thinking to solve a tactical problem. Complexity threshold isn't about token count or topic difficulty. It's about whether the task requires adaptive decision-making mid-execution. If the answer is no, you don't need an advisor. And that distinction is the entire decision framework for the adoption question we'll address in the final chapter. Let's map where this pattern is actually generating ROI in production environments. Not theory, not toy demos. The highest value deployments cluster around 3 categories. First, long horizon research agents. Think competitive intelligence tools, academic literature review systems, due diligence pipelines, anything where the task takes 10 to 60 minutes of human expert time to execute manually. The advisor pattern handles the strategic decomposition that makes these tractable. Second, multi-step data pipelines where schema discovery, transformation logic, and validation all need to be coordinated. The planner figures out the sequence. The executor handles each transformation cheaply. Third, iterative code generation loops, not one-shot code completion, but multi-turn debugging and refactoring cycles where the plan evolves. 3 clusters share one thing. The task duration and complexity justify the planning tax. And here's the signal for your own use case. If you can't map your workload to one of these clusters, you should be skeptical before refactoring. Now let's address the community concerns head-on. because the Geek News thread on this pattern raised some pointed critiques that deserve honest answers, not marketing responses. The top concern: what happens when Opus generates a bad plan? The honest answer is that bad plans cascade. If the strategic decomposition is wrong, every haiku subtask executes correctly, but produces garbage in aggregate. This is the single biggest failure mode, and it requires plan validation logic before execution begins, something most tutorial implementations skip entirely. Second concern: haiku mid-loop failures. When an executor step returns a low confidence or malformed result, does the loop recover or does it silently corrupt the context? This requires explicit failure detection at each step. Third, is this stable for production? The answer is, it can be, but it requires significantly more defensive engineering than a single model call. The pattern is not a drop-in replacement. It's an architectural commitment. If you're not prepared to build the guardrails, the single model approach is more reliable. That's the honest production verdict. Finally, let's zoom out and put this in the broader industry context, because the advisor pattern isn't a Claude-specific idea. OpenAI has been pushing GPT-4 as the orchestrator with GPT-4 Mini as the executor. Google's approach uses Gemini Pro for planning, with Gemini handling the high-frequency execution steps. The underlying principle is identical across all three providers: separate expensive strategic reasoning from cheap tactical execution. What differs? The cost delta and the capability gap. Claude's Opus to Haiku gap is currently the widest in terms of raw reasoning capability difference, which is why the pattern yields the most dramatic results on Claude. On the OpenAI stack, 4 and 4 Mini closer in capability, so the gains are more modest. The takeaway for a multi-provider architecture: this routing strategy is not a vendor-specific hack. It's a fundamental pattern for cost-efficient LLM orchestration that will only become more important as model tiers proliferate. This is the trend that the final chapter's adoption decision must account for. And the decision framework we'll give you is deliberately provider agnostic. All right, we've covered the theory, the benchmarks, and the failure cases. Now comes the only question that actually matters to you as a practitioner. Should you refactor your existing agent right now, today? Before you touch a single line of code, run through these 5 questions. First, is your task genuinely decomposable into a planning phase and an execution phase? If the answer is no, the advisor pattern adds complexity without reward. Second, are those subtasks meaningfully independent? If every subtask requires the output of the previous one in a tightly coupled chain, you lose the parallelism that makes haiku fast. Third, what is your current monthly API volume? Below roughly $500 a month in Opus spend, the refactor time almost certainly won't break even within a quarter. Fourth, do you own the prompt layer, or are you locked into a framework abstraction that hides token routing? If you can't control which model receives which message, you can't implement this pattern cleanly. Fifth, how stable is your task schema? If the planning output changes every 2 weeks due to product churn, you'll be maintaining 2 complexity surfaces instead of 1. Score yourself honestly. 3 or more green answers means you are a strong candidate. Fewer than 3 means you should wait. And I'll show you exactly why that threshold matters in the ROI math coming next. Let's put actual numbers on this decision, because gut feel is how engineering teams waste months. Here is the ROI formula stripped to its essentials. Take your current monthly OS spend, let's call it MESE. In a well-implemented advisor pattern, Opus handles roughly 10 to 15% of total tokens. The planning calls. The remaining 85 to 90% shifts to Haiku. Haiku's input token price is approximately 20 times cheaper than Opus's as mid-2025. So your projected new monthly cost is M multiplied by 0.2 plus M multiplied by 0.88 divided by 20. Work that out and you land at roughly 16% of your original spend, meaning you keep 84% of that money. Now, what does the refactor cost? For a mid-complexity agent, 1 orchestrator, 4 to 6 tool calls, existing test coverage, budget 3 to 5 engineering days. At a blended senior developer rate of $800 per day, that's $3,000 to $4,000 in opportunity cost. Divide your monthly savings into that number and you get your break-even in months. For a team spending $2,000 a month on Opus, break-even hits in under 3 months. At $5,000 a month, you're break-even in 5 weeks. The math is not subtle, but only if your checklist score was green. A yellow score means that break-even stretches past 6 months, and at that point, the opportunity cost of not shipping features is the real risk. Before we close, let me compress this entire lecture into 3 principles you can write on a sticky note and put next to your monitor. Principle 1. Assign model roles by cognitive demand, not by habit. The reason most teams overpay is not ignorance, it's inertia. They picked Opus when they started, it worked, and they never questioned it. Every prompt you send to a frontier model should earn that privilege by requiring genuine strategic reasoning. If it's pattern matching, retrieval, or formatted output generation, it does not earn that privilege. Principle 2. Measure token cost per task tier, not per API call. Aggregate billing numbers hide the inefficiency. The moment you instrument your agent to log which tier of task consumes which percentage of tokens, the waste becomes visible and fixable. You cannot optimize what you have not measured at the right granularity. Principle 3. Iterate on the plan schema before you scale. Planning prompt, the structured JSON contract between Opus and Haiku, is your highest leverage artifact. 1 hour spent tightening that schema saves 10 hours of downstream debugging as volume grows. Get the schema right at low volume, then scale with confidence. The 3 principles are not Anthropic specific. They apply to any multi-model architecture, any provider, any framework. The advisor pattern is the concrete implementation. The principles are the durable mental model. Here is where I leave you, and where your next optimization unlocks. We have spent this entire lecture on the advisor pattern, the architectural split between a thinking model and an executing model. That alone gets you to roughly 10 to 16% of your original cost. But there is a second lever sitting right there in Anthropic's documentation that almost nobody is using in combination with this pattern, and it compounds the savings further. It's called prompt caching. When Opus writes a plan that shares a common some prompt prefix, think of a long tool schema, a style guide, a domain knowledge block. That prefix can be cached server-side. You pay for it once, and subsequent calls to Opus that hit the same prefix cost 90% less on those cached tokens. Stack the advisor pattern on top of prompt caching, and you are no longer talking about 10% of original cost. You are talking about 5 to 7%. The next video in this series goes deep on exactly how to structure your prompts to maximize cache hit rate, including the one ordering mistake that silently destroys your cache efficiency and sends you back to full price. If you walked away from this lecture thinking about cost, that next video is not optional. I'll see you there.